All right, well, hello everyone, and welcome to the March AstroCheminar, the monthly seminar series hosted by the American Chemical Society Astrochemistry Subdivision with support from the Physical Chemistry Division. I'm Kyle Crabtree, I'm Vice Chair of the Subdivision, and I have a couple of announcements before we get to the talks today. The first announcement or reminder that I want to give is that the nomination deadline for the ACS Astrochemistry Dissertation Award has been extended until Monday, that's the 15th. So if you know someone who submitted their dissertation in the past 2 years, they are eligible to be nominated, and please get those nominations in to us by Monday. The second announcement that I have for you is that next month we will not be holding a regularly scheduled AstroCheminar because of the ACS Spring National Meeting. We want everyone to participate in the Spring National Meeting. We have an Astrochemistry Symposium organized by Martin Cordner and Chris Bennett titled Astrochemical Complexity in Planetary Systems. So we want to encourage all of you to attend that symposium. So that means that our next AstroCheminar is going to be on May 12th. So the second Wednesday of the month, as usual, we'll be back in the month of May. And so keep an eye out at about the first week of May for updates and more information. In the meantime, please do submit abstracts for contributed talks. This is a great opportunity for especially graduate students and postdocs to be able to present their research to the astrochemistry community. So we're very much like to see your submitted abstracts. You can submit those from the link on the AstroCheminar website. So with that, I think that's all the preamble I have for you. Let's go ahead and get started with the talks. So as our speakers are presenting, I want to direct your attention down to the Q&A tab. You can open that up and feel free to submit questions using the Q&A interface at any time. You can also post them in the chat if you're interested in using the chat instead, and we will get to those after the end of each talk. So our first speaker today is Brent Westbrook. Brent is currently a second-year graduate student in the Computational Astrochemistry group at OleMiss, led by our past chair, Dr. Ryan Fortenberry. Brent obtained his bachelor's degree in chemistry from St. Edward's University in Austin, Texas, where his undergraduate research was on the formation of covalent bonds to isolated water and hydrogen sulfide molecular cations, as well as molecular dynamics of water in carbon nanotubes. He's written several computational chemistry programs aimed at unifying high-level anharmonic vibrational frequency approaches into a user-friendly format, and he hopes to continue developing software for solving real-world problems after he completes his PhD. And so the title of his talk is Anharmonic Frequencies for the Detection of Large Molecules in Space. And Brent, you're welcome to start screen sharing and begin your presentation.
Okay, thank you for that introduction. I'll make this full screen. There we go. As you said, today I'll be talking about anharmonic frequencies for the detection of large molecules in space. The first thing I want to do is kind of clarify what I mean by large. So here at the left, you can see what we've been considering a large molecule in ammonia borane. So that's about 8 atoms. What we'd really like to move up towards are things like benzene, which are large in single quotes. That's getting closer to what you may conventionally think of as large. But really, in the end, what we'd like to get up to are things like polycyclic aromatic hydrocarbons like Ovalene at the far right. So, and also how that relates back to the anharmonic frequencies is, since our target is really PAHs, because they're nonpolar, it's going to be difficult to detect them with rotational spectroscopy. So the focus of this talk and of my research recently is mostly on anharmonic frequencies. So with that in mind, I'll give a general overview here of what a quartic force field is, since that's how we actually go about computing anharmonic frequencies. So this is kind of the fundamental equation of quartic force fields. They are, of course, fourth-order Taylor series expansions of the internuclear potential energy. And I'll just kind of quickly summarize what the terms here are. So the F terms are our force constants, or our partial derivatives of the potential with respect to the coordinate system, which we can also expand here. So that middle piece there is how it might look really in the Taylor series expansion. But then how we actually compute the force constants is using central finite differences. So you can see here, it's actually constructed out of 4 single point energy calculations. The other part there are the delta, and those, of course, are displacements to our equilibrium geometry. At the left, you can see a water molecule in its kind of optimized form. And then if I apply two of these deltas or displacements in the y direction for the rightmost hydrogen atom, that'll give us a new energy, and we can use that to compute force constants. Of course, we have to do this for all combinations of I and J. This is just one example. So as I mentioned previously on that slide, that was a Cartesian coordinate displacement. But what we've typically done in the past when we're computing coordinate force fields is to use what are called symmetry internal coordinates. Now, symmetry internal coordinates, or SICs, or SICs, as we've kind of taken to calling them recently, are composed of simple internal coordinates such as bond stretches or bending angles like these. If you take linear combinations of those simple internals, you end up at symmetry internals such as these shown below. And you can see here, the benefit of using symmetry internal coordinates is it reduces us from having to handle all 3 n coordinates as we would do in Cartesian, so 3 XYZ coordinates for each atom. Here we're down to 3 n minus 6, or the same number as the vibrational frequencies, which is only 3 coordinates for water. And that's really helpful because the scaling of coordinate force fields is geometric with the number of coordinates. Now, related to that scaling is our choice of methodology for actually running coordinate force fields. All the work I've done has been with what we call F12TZ coordinate force fields. So that's using explicitly correlated CCSD parentheses T with the F12B modality with the CCPVTZ-F12 basis set. Now, what that gives us is a really drastic reduction in the cost relative to more expensive composite methods such as CCCR that Dr. Lee mentioned briefly last time. And this still gives us anharmonic frequencies within about 5 to 7 wave numbers of gas phase experiment. The only real downside of using F12TZ, other than the slight performance decrease for the frequencies, is that it gives us worse rotational constants. But again, if we're actually interested in PAHs, we're not that interested in the rotational constant anyway. So that's not a big problem. What is a problem for us using F12TZ coordinate force fields is the determination of the internal coordinate systems. So the water example is a bit overly simplistic because as we move up towards larger and larger molecules, when we have more atoms, we have more internal coordinates. And the simple internals usually are straightforward, but figuring out how to combine them into a good description of the potential energy surface through symmetry internal coordinates can be quite difficult. So we can step outside of that requirement if we just use Cartesian coordinates directly. So that's kind of the focus of my recent research. And the first application of our methodology of using Cartesian coordinate force fields was applied to ammonia borane. So you can see here most readily in the last row of the column, or the last row of the table, excuse me, how our coordinate force field results compared quite favorably with the 7 available gas phase experimental results. So the previous theoretical results had a mean absolute error of 24 wave numbers compared to the experiment, whereas ours only had 5 wave numbers. So again, as I mentioned before, we kind of expect F12TZ coordinate force fields to have an error of about 5 to 7 wave numbers from gas phase experimental results. So this suggests to us that our Cartesian coordinate force fields performing at least as well as our symmetry internals. The other interesting aspect of this paper actually was how important it is to take into account resonance corrections when doing these anharmonic frequency calculations. So you can see what I've called our unperturbed, and we'll actually focus in on nu 5 here, since that's the B in stretching frequency. So you can see what I've called our unperturbed value at the far right here of 631 wave numbers actually agrees quite well with the previous theoretical computation. But when we take into account the type 1 Fermi resonance between 2 nu 6 and nu 5, it actually increases our frequency by 13 wave numbers. Now, the intensity of this mode is pretty low, so it hasn't actually been observed experimentally before, at least in the gas phase. So we're hoping that our 644 wave number is going to be the most accurate available data for that mode. So as I mentioned before, talking about the 3n versus 3n minus 6 coordinates, the main problem with our Cartesian QFFs is how slow they are. So they require way more points to run. And so our work right now after the ammonia borane paper is trying to figure out how we can speed those up. One obvious way to do it is to actually account for some types of molecular symmetry. So here I've just drawn a simple example in water. When we stretch that left hydrogen out to the left, that's symmetry equivalent to doing the same thing on the right. And you can also think about any of the in or out of plane motions of the water molecule. Those are going to be the same as the mirror image. So we should be able to drastically cut down the number of points just from taking advantage of that symmetry. So I'm currently working on trying to implement that. Eventually, I would like to automate actually the determination of the symmetry, which might help to feed back into our symmetry internals as well. Because again, the reason we don't just use symmetry internals from the start is because it's difficult to come up with the internal coordinate. Now, a more exciting way we can approach speeding up the force field is to use analytic derivatives. Here I've reproduced the finite difference equation for the second order force constant from earlier using energies. And then I've shown it again using only analytic first derivatives or gradients. And you can see already that we've gone from having to do 4 single points down to only 2 in the bottom part. But what may not be as obvious is that the top formula is giving us a single force constant, Fij, because both I and j are fixed in the right-hand side of the equation. Whereas with the gradients, we get a lot more information. So for a given I, we actually get all the j force constants. Now, this is even more pronounced when we go up to higher derivative levels. And really, the strength of the gradients is converting our problem of having to compute a 4th order force field in terms of energies down to a 3rd order force field in terms of gradients. Because the 4th order finite difference formulas, in the worst case, would basically take up the whole slide. So they make up the vast majority of our quartic force field computation. So if we can reduce the derivative level, that's a big win in the number of points, as you'll see in a couple of slides. Now, another promising aspect of using analytic derivatives is relates back to Dr. Lee's talk from last week again, where he discussed the out-of-plane bending issue for multiply bonded hydrocarbons. So as he pointed out, nobody really knows exactly what's going on there. We have seen in the past that the issue can be alleviated somewhat by changing the step size in our quartic force field. So we're thinking that analytic gradients may help in this aspect because they can eliminate one of the finite step sizes from the quartic force field. So that thinking kind of informed our choice of molecules for our analytic gradient investigation. You see here we've got 3 hydrocarbons that have previously exhibited the OPB issue. On the left, we've got acetylene, then cyclopropionylidene, and then ethylene at the far right. Obviously, these as hydrocarbons relate back to our eventual goal of looking at PAHs as well. However, before we started actually looking at the analytic gradients, we realized there were a couple of problems. We typically run all of our quartic force fields in MolPro. And when we looked into using the gradients, we saw, at least in the version we had access to, that all of the CCSD parentheses T F12 gradients use density fitting. And then we also noticed that the density fitting algorithm currently only ran in C1 symmetry. So we, again, didn't find either of these too troubling, at least at face value, because many of our Cartesian displacements are going to end up in C1 symmetry anyway. And we thought, if anything, the density fitting may actually speed up the calculations. With that in mind, we did want to try to disentangle the confounding factors there. So we wanted to run a symmetry internal coordinate just as a baseline, since that's kind of our tried and true method from the past. Then we wanted to try to evaluate the cost of turning off symmetry in the individual MolPro calculation. So we ran our same symmetry internal formulation, but just turning off symmetry directly in MolPro. Then we finally introduced the density fitting itself with our symmetry internal formulation before moving on to Cartesians, density fit Cartesians, and eventually our density fitted Cartesian gradients. So you can see already some of the troubling results we found. So our original plan was just to run a single quartic force field with each of those 6 treatments on each of our 3 molecules. So I started off running symmetry internal coordinate QFFs on cyclopropionylidene, and you can see the results in the first column. Then I went and did the Cartesians, and you can see there are some differences between the SIC and Cartesian results. But as you'll see in the summary table, overall they seem to have comparable accuracy, which is what we had hoped for and expected based on the ammonia borane results. Where trouble really started to crop up was when I first used density fitting. So you can see here in the first run of the density fitting, especially in modes 6 through 9, there are some substantial differences between the 6, the carts, and the density fitted 6. So actually, it was kind of so bad that I was afraid my code was malfunctioning. So I decided to run another test, the second run of density fitted 6. And this is where the real problems show up, is we get different answers from the first run and from the other 2. And this is totally counter to what we expect from quartic force fields, where if we think if we give it the same input, we should get the same output deterministically. So I decided to go ahead and run 5 runs of each methodology. And we then averaged those and took the range across the 5 runs. So here I'm reporting the data for the 5 runs on density fitted symmetry internal coordinate QFFs for cyclopropanolidine. I'm also reporting what I've called the true value here. So that's a combination of argon matrix experimental data from Huang et al. Down below, and where that was unavailable, some high-level computations from Dr. Fortenberry. Then the average column again is just averaging across the 5 runs. Then the range column is taking the difference between the highest frequency reported for a given mode and the lowest. So you can see these two I've highlighted in red actually differ by more than 200 wave numbers across the 5 runs, which is quite concerning. And then delta finally is just the difference between the average and the true. And then to condense that even further, I took the mean absolute error of all the ranges and all the deltas, and that's what's going to be reported in the next table. So you can see here is our summary table. Again, you can see the performance of the density fitting is quite poor, with average ranges of greater than 30 wave numbers everywhere except the density fitting on acetylene. So that one's actually surprising in that it doesn't have a large range like the others. Now, as I mentioned before, we'd expect all these ranges to be 0 to get the same results each time. And our conventional symmetry internal coordinates, and as well as the newer Cartesians, come very close to that ideal. In the worst case, they differ by about 0.1 wave number or 0.3 wave numbers on average. In contrast, you see with the density fitting Cartesians, starting with ethylene, a range of 64.5 wave numbers, and many of the others, or all the others besides, again, the density fitting internal coordinates for ethylene are greater than 30 wave numbers. When you look at the density fitted gradients, we see some improvement, but it's still not as tight as we would like, especially compared to the symmetry internals in the Cartesians. But where this really was disappointing for us, besides the anomalous instability in the frequencies themselves, was in the timing. As I mentioned before, the whole reason to look at gradients for us was really to speed up our Cartesian coordinate force fields. And it's perhaps clearest to see this in the relative time column, where I've divided the absolute total wall time for all the jobs by the lowest for a given molecule. So in all cases, I've divided by the symmetry internal coordinate timing. So you can see symmetry internal coordinates are our fastest. When you turn off symmetry, it slows it down by about a factor of 1.5. But when you add the density fitting, it slows it down by a factor of about 5 or 6. So it seems like some aspect of the density fitting is slowing down our calculations substantially. This is obvious again when you compare the Cartesians and the density fitted Cartesians, which again have the same number of points, and the density fitted Cartesians are between like 3 and 5 times slower. The gradients do improve somewhat over the density fitted Cartesians, as we would expect by the dramatic decrease in the number of points, but it's still not enough to make them cheaper than actually doing the Cartesians themselves. So that's some troubling data. But obviously, we're not giving up on analytic derivatives in general. It just seems potentially the implementation we have access to right now may not be ideal for our purposes. For all the reasons I mentioned earlier, the OPB issue, the speeding up, the reduction in the number of points, we're hopeful for analytic derivatives moving forward. And with that, I'd just like to acknowledge all of my lab mates and the funding agencies and Dr. Fortenberry. So thank you. And with that, I'll be glad to take any questions.
All right, thank you for that talk, Brent. If there are any questions, please go ahead and open up your question and answer panel and go ahead and submit them. And while right now I don't see any questions in the chat or in the Q&A, but I do have a question that I will defer actually now that one question has popped up. So, and this is my question as well. An anonymous attendee is asking if they understand correctly, the density fitting is not deterministic. And can you elaborate on what the possible reason for that might be?
Yeah. Well, that is kind of the open question for us as well. Yeah, because that was very surprising. Probably our best guess. So I showed the finite difference formulas. That seems like one place where this kind of numerical instability can crop up. That's kind of what we've seen in the past, even with relating to the out-of-plane bending issue. Because if you run just a single point energy with density fitting over and over, you do get the same energy. So I think we're thinking that it may just not give you as many significant figures consistently. Something like that.
Yeah, I guess to follow up on that, like, have you tried to track down like which particular force constants vary so much that give rise to these very different frequencies? Like, is there anything systematic about which force constants are affected?
No, we haven't looked into that yet, but that's a good idea.
All right. Other questions? Please go ahead and type them in. In the meantime, I'll ask. Can you say a little bit more? I know this is not I think it's a fairly standard thing, but can you talk a little bit more about what you did for deperturbing the resonances in? I can't remember the molecule now, but yeah.
Oh, in ammonia borane. Yeah.
Yes.
Well, so we used this program called Spectro to actually compute our frequencies from the force constant. And so it's kind of a black box. You basically, the first time you run it, it tells you what resonances are present, and then you can tell it again to actually treat them. So in the first case, for the so-called unperturbed values, I'm just reporting the frequencies without handling any Fermi resonances. And then the second one is just actually accounting for it.
Yeah, I guess one other question is what are the next steps? Like what is the next thing that you need to solve in order to get along the way to PAH treatments?
Yeah, I think symmetry is really the big one. We were hoping gradients would help a lot, but as I pointed out, the current implementation we have access to doesn't seem that promising. So what I'm actively working on now is actually handling those symmetry considerations.
Hi. We have another question in the chat from Juan Camilo Zapata. He says, thanks for the talk. I was wondering, how likely do you think it would be to expand the method to density functional theory calculations as well?
Yeah, I mean, that's totally doable. We haven't really done that in our group, but I know some other groups do these types of calculations using density functional theory. Yeah.
All right, well, I don't see any other questions right now, and we're about at the end of the time for the first talk. So thank you again, Brent, for that very nice talk. We're going to move on to our next speaker. And our next speaker today is Professor Brett McGuire from the Massachusetts Institute of Technology. So I have known Brett for quite a long time. He did his undergraduate studies at the University of Illinois at Urbana-Champaign, where I did my PhD studies. We were both in the group of Ben McCall, and I went back to the archives, and I found this nice classic photo from way back when we were graduate students, when we got a chance to go visit the Green Bank Telescope. So there was Brett as an undergraduate visiting the GBT for a workshop that was put on. It was a really formative experience for me, and probably for Brett as well. So just took that trip down memory lane as I was preparing for this introduction. So after finishing his bachelor's degree at the University of Illinois, he went on to do his PhD at Caltech on terahertz time domain spectroscopy of interstellar ice analogs and radioastronomical observations of complex organic molecules. After finishing his PhD, he was a National Radio Astronomy Observatory Jansky Fellow and then a NASA Hubble Fellow at both the NRAO and the Harvard Smithsonian Center for Astrophysics. And it's just this past year in 2010 when he started as an assistant professor in the chemistry department at MIT. And so research in his group is aimed at using the tools of physical chemistry, molecular spectroscopy, and observational astrophysics to understand how the chemical ingredients of life evolve with and help shape the formation of stars and planets. He also, when the pandemic started, he took the initiative to start up an online seminar series that was an inspiration for our own AstroCheminar series called the Astrochemistry Discussions. And those seminars are still ongoing on a monthly basis. They are happening on the fourth Wednesday of every month, so kind of happening opposite these AstroCheminars. So their next one is March 24th. And the topic, the theme is a photon-dominated regions (PDR). So we definitely encourage you all to check those out. And with that, Brett, feel free to start screen sharing. The title of his talk is New Frontiers in Cosmic Carbon.
All right. Thanks, Kyle. Thanks, everybody, for the invitation to talk today. Unfortunately, the way that my monitors are set up, I can't see any faces right now, so I'm talking into the ether. What I want to do today is tell everybody a story, a bit of an update on work that my colleagues and I have been doing over the last about 2 or 3 years now, examining complex carbon chemistry in the interstellar medium. And we've been doing a lot of different investigations looking at different themes around this set of molecules. Today, what I really want to focus on is the prevalence, or in some cases the lack perhaps, of carbon molecules that have rings in their structures, and why this might be a little different or appear to be different in space than the prevalence and chemistry of these molecules here on Earth. And I'll put up the obligatory slide of detected molecules in the ISM here. It's accurate as of maybe 6 months ago or so. And as you can clearly see from looking at this list of molecules, there's not all that many rings in the interstellar medium. Of course, you can't really see it on this list, so I'll put it up in graphic form here. So here I've broken down into this sort of half ring, half pie chart here, the percentage of interstellar molecules that fall into these different categories. And it doesn't add up to 100% because a lot of molecules fall into more than one category. But you'll see here that the cyclic molecules, well, they make up only about 7% of those detected in the interstellar medium. And this includes any type of ring from 3, 4, 5, 6 or more members in it. And that's quite shockingly different if you look and compare to the way that the structural motif shows up here on Earth. If you dig into the Chemical Abstract Service, this is a database of all molecules known to humanity, maintained by the ACS. You'll see that something like 80% of them contain a 5 or a 6-membered ring, and this number doesn't even count those with smaller or larger ring systems in them. So it's a really striking difference here in the number of rings that are seen in space relative to those that are seen here on Earth. And so the question that I want to ask and talk about today is, are there really so few rings in our molecular inventories in the interstellar medium? I'll move that question over there. And just to kind of forestall any suspense that you might have here, no, the chemistry that happens in space, while it's affected by the different conditions that are there than there are on the planet Earth, is not so different from what happens on Earth that we should see this huge disparity. It turns out we think something like 10 to 25% of all interstellar carbon is in aromatic rings, in those PAH molecules that we just heard all about, right? Now this number, 10 to 25%, and the actual identities of these molecules are subject to extreme variance, depending on which expert you ask for their opinion. And of course, these molecules can be both pure hydrocarbon forms, like what I've shown here. These are some of the very smallest examples. They are thought to get quite large in size. And you can substitute heteroatoms like nitrogen into these rings, and you can decorate the outsides with whatever functional groups you'd like. Add CNs, add OHs, add aldehydes, carbon chains, anything you'd like to the outside. And all of that still contributes to this total budget of 10 to 25% locked up in these aromatic type molecules. Now, how do we know that? How are these numbers being arrived at? Well, it goes back about 30 to 40 years to the original observations of what are now called the unidentified infrared bands. These are these bright and distinctive patterns of light that are seen in the infrared, primarily towards UV-dominated regions in our galaxy, and also toward the hearts of dozens, if not hundreds, of other external galaxies, as we've seen with Spitzer and other space telescopes. So if I zoom in on this here, you'll see that unlike what you might be used to seeing when you look at a spectral line survey of a source in space, say in the microwave or the radio region of the spectrum, here the lines here are not labeled by any individual molecule, right? They're labeled by stretches and bends. In particular, they're labeled by the CC and CH stretching and bending motions characteristic of aromatic molecules. And that's because while the infrared spectra of PAHs are, of course, unique to those molecules, and we could take them in the lab here on Earth, put them into a high-resolution spectrometer, and readily distinguish one PAH from another, in space, we can't actually separate our mixture out. And so we have a huge conglomeration, an aggregate of dozens, if not hundreds or even thousands of different PAH species, all emitting towards us along one line of sight. And it turns out that while these infrared bands are unique to each molecule, the CC stretch of one aromatic molecule looks an awful lot like the CC stretch of another. And so they all add up into this distinct emission spectrum, which has the characteristics of emission from aromatic molecules, but is not characteristic enough of any individual one for us to identify the underlying species. Now, that's pretty disappointing for a few reasons. One, well, from the intensities of these bands, we estimate there's a lot of carbon locked up in them, right? And so it's important to understand what that carbon is doing. And second, it means that we can't study them on a detailed chemical level. We can't understand the inventories of the 30, 40, 400, whatever have you, different PAHs and how they're reacting with one another, how they're being built up, how they're being destroyed, and how they contribute to the other molecules that we can see on an individual level. And that's kind of embarrassing for us as chemists, or it should be embarrassing for us as chemists, because we actually understand the chemistry of PAHs on Earth pretty well. And that's because they are the primary byproducts of incomplete fossil fuel combustion, and they're actually potent carcinogens that you find in the char marks on grilled meats and vegetables. So they're terrible for the environment and they're terrible for our health. They give us cancer. So we really want to understand how they're formed and how they react both in the environment and in us quite well. And it turns out on Earth, we have at least a pretty good idea of how these are formed in these high temperature environments. There's a number of different pathways, but a lot of them look something like this, where you assume that you start with a single ring like benzene, and then you successively add acetylenic subunits. So these C2H2 units here, where you bring them in, add a bond, bring in another one, add a bond, and then form a bond over. And you're just successively clicking on additional rings. Sometimes they'll be 5-membered, sometimes 6-membered, sometimes they'll come with extra decoration, as we talked about. Now, these pathways work pretty well, and we can model and study them pretty well here on Earth. But they have a problem for their application to space. And that's that each step in this process has an activation barrier. It requires energy. Now, when we're combusting fuel or when we're grilling our foods, there's plenty of energy to be had. That's not a problem. But in the cold of space, reaction barriers basically mean that these cannot go, and that this isn't a viable mechanism for building them up in basically any environment in the interstellar medium. Well, any environment except one. And this has largely led us to conclude that the most likely way that we could make these is in very high temperature environments around evolved stars. So here's an example picture of IRC plus 10216, sort of the canonical evolved star. It's right here in the center with these beautiful concentric shells of material being spewed off of it. And the thought here is that these old stars basically act like sooting candles, outputting carbon black into the interstellar medium. And in the high temperature, high density environments immediately surrounding their circumstellar envelopes there's enough energy either in the gas phase or on the surfaces of particles to overcome these barriers and build up very large PAHs very close into the center. Now, as that material is ejected, those PAHs stop being formed and instead start being degraded by the UV radiation given off not only by the star, but by the background interstellar field. And they start getting broken down into medium-sized PAHs and small PAHs, and eventually down into the single benzene ring, and perhaps a little bit further, although benzene itself is pretty stable. So then these molecules freeze out into some distribution of small, medium, and large. They traverse the interstellar medium until they wind up in some sort of UV-dominated region like a PDR or a star-forming region, where they absorb that UV radiation and then re-emit it back to us through fluorescent transitions in the infrared. Those are those unidentified infrared bands that I showed you a couple slides ago. Now, this picture fits pretty well. right, we can assume that the chemistry works because it seems similar to what would happen here on Earth. And in fact, observations of these molecules seem to show that their presence in these regions is quite likely. We can see this sort of emission around old stars and planetary nebulae and those sorts of regions. But there is another possibility, right? We could assume that we start with very small molecules in cold, dark clouds where there aren't any stars, and through some pathway that is not equivalent to what happens here on Earth, right, build up that first aromatic ring, and then successively build up larger and larger molecules from the ground up. This, of course, would have to be through pathways that don't operate requiring high temperature environments. So maybe ion molecule pathways or some other neutral pathways that we haven't considered yet. There's not a lot of work on this, unfortunately, because the environments where this matters on Earth are all high temperature for the most part. So these two different pathways here have come to be known as the top-down and bottom-up approaches, because in the top-down, you build up the large ones first, and then you degrade them. And in the bottom-up, you start with the small things and build up larger. So if we want to actually look into the chemistry here, the relative difference between these two, it seems like the logical place is to start at the bottom of the top-down or the bottom of the bottom-up with benzene, right? This seems to be the common link between the two, or other small molecules like benzene. And in fact, we have attempted to do that. We've attempted to go look for benzene at a bunch of different locations in space, but unfortunately, it's quite difficult. Benzene has no rotational spectrum. The only way we can look at it is in the infrared. And here is its strongest transition, the one that we would want to go after. It's the new 4 bending mode, a little short of 15 microns here. And behind it in gray there, that's the opacity of our atmosphere. And in fact, that's the opacity of our atmosphere as measured from SOFIA, a telescope on the back of a 747 running at about 45,000 feet. It's a brick wall. It's just impossible to observe this strong transition of benzene, this strongest transition of benzene from the ground. So we have to rely on space-based infrared observatories, of which we had a couple. And so we do have a few detections of benzene in space. So the first one from Pepe Chernacharo back in 2001 towards CRL 618. It's this little dip right here. There's the new 4 bending mode, again, just short of 15 microns. And then about a decade later, we got this really nice detection in the Large Magellanic Cloud nearby from Malik et al. And then there's reports of 2 more detections here in this conference proceedings, which I've been unable to find a peer-reviewed publication for since. But they claim detections in both of these sources. So we have, what, 2.5 detections here of benzene in space, which is great. But if you're like me and you don't memorize the telephone book number of these sources here, I looked them up, and these are all pre-planetary nebulae or post-AGB stars. They're all these high-temperature environments where we would expect to find PAHs in this top-down methodology, where we already have observational evidence of them being present. So that really doesn't help us in probing these 2 different pathways as possibilities here, at understanding how PAHs might be formed. So we wanted to see if we could find another environment where we could look at these large carbon molecules that might favor the bottom-up pathway, or at least allow us to probe it in more detail. And if you want to look for carbon molecules in space outside of IRC plus 10216, the best place to do it is a source called TMC1. It's a cold, dark, starless core located in the Taurus molecular cloud. That's this dark, dusty vein here in the sky as seen from my apartment complex in Charlottesville here. And the way that you want to do it is not with infrared astronomy, right? And that's because this is a cold, dark cloud. It's really hard to get a lot of photons through to do the absorption spectroscopy. And besides, since it is cold, most of the population here is going to be most easily probed using low energy rotational transitions in the microwave or radio regime. So we want to use the most sensitive radio telescope that we have for this. That would be this behemoth here, the Green Bank telescope that we saw the picture of early on. That picture that Kyle showed at the beginning actually is the first time I ever set eyes on the Green Bank telescope. It was at a conference put on for, I believe, the Center for Chemistry of the Universe, which was at UVA for several years. A really fantastic experience, my senior year of undergrad. And I have been using the GBT ever since. It's a really fantastic instrument. Now, I said that we wanted to look at benzene here to start with, and there it is. Well, no rotational spectrum, right? It's a completely symmetric molecule. So it's really difficult to look at with a telescope like the GBT. In fact, it makes it a pretty bad molecule to go after in TMC1. But we're chemists, and we can say, well, TMC1, if it has benzene, we know it has an abundance of cyanide, CN, and if those two come together and react, they should form this molecule, benzonitrile. Now, this has a whopping dipole moment. It has really strong transitions, especially at the cold temperatures of TMC1, about 10 Kelvin, down in the range of the GBT. So this would be a perfect candidate to go look for. In Mike McCarthy's group, I measured the spectrum of this molecule some years ago. And then to make a long story short, back in 2018, we published the detection of this molecule in TMC1 using the GBT. And I show here a number of our strongest and most well-detected transitions, some of them which have pretty high signal to noise, and some of which, well, you have to have very loving eyes to see that are there. But we have quite a number of these here in the pattern, and it was a nice firm detection. So this was fantastic, right? We have now a handle on an aromatic molecule seen with radio astronomy in a source that's not one of these post-AGB stars. But the question then is, what do we do with this, right? What can we learn from this? Where do we go next in order to understand the chemistry that's happening here and the implications on that larger picture of aromatic chemistry that we were talking about at the beginning? And for that, we need to answer a few more questions, and I've put them here. The first is, can we tell whether or not this benzonitrile or other aromatic molecules, if they're present, are built up in situ? So are they made from the bottom up in TMC1? Or are they inherited from some prior generation of AGB star population? And second, are there other aromatic molecules in TMC1? I mean, we're going to do further observations of the source, so of course we're looking for new molecules in general, but we're really interested in other aromatic or other ringed molecules in this source so that we can explore the full extent of this chemistry. And finally, is the chemistry that we're seeing here, or at least we think we'll see here with benzonitrile, unique to TMC1? Because if it is, this is the only place in our galaxy where we're seeing it, well, then it's interesting from a purely chemical view, but it's not very impactful on the overall picture of molecular evolution. It's not very impactful on our understanding of how this carbon evolves through the process of forming stars and planets, if it's just a unicorn in this source. So I put together a large collaboration to try to answer these questions. If you know anything about astronomers demand that all projects begin with an acronym. So our project is called GBT Observations of TMC1, Hunting Aromatic Molecules, or Gotham. This would be our legally dissimilar logo made from actual benzonitrile data there up at the top that we're very proud of. But I'm even more proud of our collaboration that's grown quite a bit over the last couple of years and is led by a team of co-PIs that help me out here that are really just fantastic. So we can be broadly divided into 3 different subgroups. Our observational subgroup is led by co-PI Andrew Burkhart, who's an SMA fellow at the Center for Astrophysics. Our laboratory subgroup is led by Elsa Cook, who is a Marie Curie fellow at University of Rennes. And our modeling subgroup is led by co-PI Siju, who is a senior graduate student at UVA. And you can see here just a really fantastic team from many different institutions, different continents, different career stages. And because this is astrochemistry, of course, we do move between these categories somewhat frequently. So what I want to do today in the remainder of the time is to give you a brief overview of some of our initial results from Gotham and our investigations. And these all hinge around our current primary data product, which is a high sensitivity, high resolution spectral line survey of TMC1 with the GBT. You can see down here around 18 to 20 gigahertz, these choppy little regions. This is the data that we took to detect benzonitrile back in 2018. And we've been gradually trying to fill in higher and lower in frequency, doing a complete spectral line survey of the regions that are accessible given largely the weather constraints at the GBT. The goal here is to explore the full chemical inventory of the source, do it at sufficiently high resolution that we can pick apart the different velocity components that are present here and the individual clumps of molecules, and then learn something about TMC1's chemistry as a whole. So let's take a look at the observations to start with and see how much they have improved over our early observations. So here again are the lines of benzonitrile that we published with the first detection. And then over here on the right, I'm going to put up our benzonitrile lines, the best ones that we have from our new data. Of course, we have many more than these. We have something like 50 or 60 that are detected above 3 or 5 sigma now. And you can see that the line profiles themselves are just gorgeous. We have not only resolved hyperfine splitting from the nitrogen, but we have multiple velocity components because the TMC1 is not a single cloud. It has multiple clumps in its substructure, and we see it all at fairly high resolution. Now, I do want to use this as an example to lead into a data processing technique that we have developed, particularly in the area of determining the significance of a new molecule detection, or how much evidence there is for the presence of a molecule in a source. So let's have the thought scenario here for a second that we have two different sets of data here on the left and on the right, and these are all the lines that we have for benzonitrile. Which one of these is the better detection of benzonitrile? Well, it can be a little hard to say just from your gut instinct, right? Because the lines on the right, these four, well, they're really high signal to noise. There's only 4 of them. There's only 4 pieces to that spectral pattern that we use as our fingerprint for this molecule. On the left, well, these are much lower signal to noise, but we have far more of them, substantially more of them. So it becomes a little bit of a challenge here to say which one of these is the better detection. And in fact, it becomes a challenge to say what's the significance of the detection? Is the significance the signal to noise of the strongest line? Is it the signal to noise averaged up of the strongest 5 lines? It's kind of hard to say. So we wanted to come up with a way to put a number on it, as well as to increase our ability to detect weak molecules. And what we're going to do, and now I'm going to be focusing on our strong lines here on the right, is we're going to say, all right, let's pick out our lines one by one and center them all at 0 kilometers per second of relative Doppler shift. And so here's our strongest one. It's 12.5 sigma. Then what we're going to do is we're going to center all of the other lines at 0 kilometers per second as well and average them together. All right. So we will no longer have a spectral pattern for benzonitrile, but we will have an average signal of the benzonitrile molecule all together at a central Doppler shift velocity of 0 kilometers per second. And we do it weighted by the signal to noise and the intensity of the line. The red line here is our model where we have the source components and a standard radiative transfer model, and the gray behind is the data. So I'm just going to play a little animation here. You'll be able to see how our signal from benzonitrile, not the spectrum of benzonitrile, but the signal of benzonitrile now evolves to higher and higher signal to noise as we average more and more lines together. Now this will start to plateau at some peak signal to noise here, because of course now we're averaging weaker and weaker lines in. There's still signal, so it will still increase, but it's going to go a little slower. And you'll see here that as we top out at 50 lines or so, we're going to top out a significance of 28.1 sigma. That's the peak significance in this central channel. And I can show you if we average all of our lines, because we have about 1,000 of them total covered, we can get up to 28.3 sigma. So not a big gain once you go past the ones that we detect very well. So here we have our average stacked signal from benzonitrile in the source. But this isn't actually still the significance of the detection, right? This is the significance of the detection, the signal to noise in that central channel, or a little lower in the channel next to it, or a little lower in the channel next to it. But this is all information. This is all information content on the presence of benzonitrile in this source. And we've done an awful lot of work with our model here to model the 4 different velocity components and the width and splitting due to the nitrogen hyperfine quite well. So we want to be able to find a significance that bears in mind, that keeps in mind, that accounts for the full width, the full information content of this signal. So what we're going to do is we're going to borrow a technique from the radar community developed some 50 or 60 years ago called matched filtering. And this is a technique that was applied quite recently by Ryan Loomis to spectral line observations in protoplanetary disks, and that he helped adapt to apply to our observations with the GBT. So what we'll do is we'll use our model, All right, the model of emission that we have generated for this molecule in this source is a filter that will push through and correlate with our data and record the response of. You can see here at the center, this response signal now contains all of the information of both the intensity of the line and its profile as it moves through this signal. And so this presents an impulse response, which is the significance of our detection in this source. So 53 sigma detection of benzonitrile in the source, which is just really nice to have a number to put on how confident we are that our model, that the molecule is there at these different levels and in these different velocity components, is correct. So I'll show you one application here to a non-cyclic molecule first. This is Propargyl Cyanide, which we reported the first detection of in Gotham earlier this fall. We have a number of individual rotational lines that we see, a little lower signal to noise than the benzonitrile, but they are here. Again, we can model the velocity components and the hyperfine splitting quite well. But we have many more lines than this, just like we had many more lines for benzonitrile. There's several dozen of them. We can add up into a stack and then push through in a filter to get an actual significance to the detection. So there's a little under 21 sigma of evidence that this molecule is present. So how does this actually apply to cyclic molecules, and what cyclic molecules are we going to look for? Well, to come up with new candidates, what we did was our team members, Mike McCarthy and Kelvin Lee, along with some members of Mike's lab, just took benzene and blew it up in a discharge with nitrogen in their microwave spectrometer at Harvard and recorded the signal that came out, did a line survey in the laboratory. And using some really fantastic new techniques developed by Kyle and some Python tools developed by Kelvin, they were able to identify more than 100 different products, including many that had never had their microwave spectrum measured before, among which were these two, 1-cyanocyclopentadiene and 2-cyanocyclopentadiene. All right, these are 5-membered rings, so that's interesting. And we went and looked first in our early data, going all the way back to observations taken through May of 2019, and we couldn't see any individual lines, but our stack and filter showed us that there was evidence for 1-cyanocyclopentadiene at the almost 6 sigma level, and no evidence for 2-cyanocyclopentadiene. Now, as our data collection continued and we go 1 year forward to June of 2020, right, we have higher signal to noise data. We now have a higher signal to noise detection of the 1-cyanocyclopentadiene, a full detection at 6 sigma of the 2-cyanocyclopentadiene. And in fact, our model here predicts we should be able to see individual lines of 1-cyano. And in fact, we can now start seeing them come in here in the data, which is great. And these are the first 5-membered rings ever seen in space, which is exciting. Even more exciting, we went after benzonitrile as a proxy for benzene. So why not go after 1 and 2-cyanonaphthalene as proxies for naphthalene, an actual PAH here that, again, not a good target for radioastronomy, but these molecules have permanent dipole moments. So their spectra was measured in the laboratory by Don McNaughton, and I'm happy to show you the results now, although these are embargoed, so please do not share them widely. They'll be published in Science in a couple of weeks here. So 1-cyanonaphthalene and 2-cyanonaphthalene in our data, we have evidence for at the 14 and 17 sigma level. And in fact, for 1-cyanonaphthalene, our data are good enough that we can see the individual rotational transitions of it now at 4 or 5 sigma in several of the lines, which is really fantastic. So these are the first PAHs ever individually identified in space, and we did it through the rotational spectra, which is exciting for us. It also means that we can start digging into their chemistry on a detailed level, and I'll finish with that over the next couple of minutes. Before I get to that, I do want to highlight that we're detecting many new molecules in this survey beyond the ones I've mentioned here, work by many of the different members of the collaboration, which are fantastic. So keep an eye out for these that have already been published or will be published soon, as these work through the peer review process. So to finish off here in the last couple of minutes, I want to talk about our use of astrochemical modeling to try to explain the presence of these. We started by borrowing an astrochemical model that is well developed, the KETA code, and using the database of reactions and molecules that it comes with. It's 800 or more species and 10,000 or more reactions, all bottled up and ready to go, of which basically none of the species or reactions that we need for Gotham were included. It's because nobody has had a reason to do the detailed modeling of PAH chemistry in space before. So we're basically starting from scratch. That's okay. A lot of the molecules in TMC1 are in this network. And so here's some results from our modeling team looking at the linear molecules, the cyanopolyeins. The traces here just show the abundance of a molecule at a given time that our model predicts. The dots and dashed lines here are the observed abundance in TMC1. We put the dots at about the age of TMC1 here. And the shaded regions is our uncertainty in the observed abundance. And you can see that our model reproduces the observed abundance for these simple species quite well, which is encouraging. It means we probably have a somewhat good handle on their chemistry. Of course, if we go look at our PAHs, we see a completely different story, unfortunately, and this is again embargoed. This is the result if we try to build 1 and 2 cyanonaphthalene up using a bottom-up route. We're 6 orders of magnitude off from the observations. And of course, we could ask, well, maybe the naphthalene is just inherited from a carbon star initially. So we could just seed our model with some abundance of naphthalene off at the start and see what happens. Well, we can do that. We put in enough naphthalene to reproduce the abundance of the cyanonaphthalines at about the age of TMC1. But you can see here that the model still sees them falling off rapidly as the source ages. And in any case, the amount of naphthalene we had to put in there requires 1% of all carbon in the entire cloud to be in just naphthalene to reproduce this abundance. So this is telling us that the models are woefully incomplete, either from the bottom-up perspective to the top-down perspective. And there's no way at the moment for us to distinguish which one, if either, is dominating. So we've got a lot of irons in the fire right now, working both theoretically and with laboratory colleagues to shore up both sides of that network. The last slide that I want to show you is to answer that final question. Are these molecules in TMC1 a chemical curiosity, or is it more widespread? For that, Andrew Burkhardt has been leading a sub-program of Gotham named ARCHM, a rigorous K-band hunt for aromatic molecules. And the goal here is just to look for benzonitrile in other sources. And we had a good deal of success here. So we've seen benzonitrile now at high significance in a number of dark clouds and serpens, as well as in one source that appears to have an active young protostar in it. So it appears that this chemistry is indeed quite widespread and may have applications far beyond TMC1. So to come back to those questions here, is benzonitrile or these aromatic molecules built up in situ or inherited? We're not sure yet. There's not enough evidence one direction or the other, but this is an entirely new and unexplored area. We have to build up the entire network from scratch. So we're working on it. Are there other aromatic molecules in TMC1? You betcha. There's a ton going on here. We think we've just scratched the surface of the molecules present in our survey, and we're still taking more data. And this chemistry is definitely not unique to TMC1. We see it in a number of different molecular clouds, meaning that it probably has implications to chemistry in the broader star and planet formation cycle. And we're excited to see where that takes us. So with that, I'll put up a slide of acknowledgements here, a word cloud of all the wonderful people that I have worked with over the years. Shout out to my postdocs, Kelvin Lee and Tim Barnum, sources of funding. And I'm happy to take any and all questions you might have.
All right, Brett, thank you for that very nice talk. A couple of questions have come in, and so I'll read you the first one from Miles Edwards, who asks, speaking from experience, it is possible to identify substances if a rigorous determination of the complex refractive index is done. Any thoughts on that approach? And this question came in while you were talking about PAHs and the UIRs.
Sure. Yeah. So my answer to that would be that we are having enough trouble right now identifying the simple components of interstellar ices, which we can observe in absorption along well-controlled lines of sight, and which are much simpler mixtures containing, say, water and methanol and CO and CO2. And the task of getting the complete, including complex portions of the optical constants necessary to do that sort of refractive index measurement is just monumental. There are several different lab groups working around the world to do that in these ices, and we still have not gotten to the point where we can reproduce interstellar observations based entirely on these optical constants. That might change with new data coming in from JWST, knock on wood, and some really nice advances in particular terahertz spectroscopy of ices. But that's where we are for that. For something as complex as the PAHs, I think that mixture is going to be such a monumental number of free variables for that, that we would have trouble backing anything out at this point. Maybe if we can get our models to a point that we are having a better handle on the types of PAHs available, we could narrow down the parameter space that we have to explore. But I think we're some years off from doing that to identify individual components, certainly.
I guess as a slight follow-up, will JWST help with this problem at all on the observational side?
So JWST should certainly help us with the identification of benzene in more sources. At least that's the hope. It's also going to give us much higher resolution observations of some of these UIRs, but I think the likelihood of picking out individual PAHs from infrared observations with the JWST is still relatively small. What it will be able to do is provide us better data to do analyses of the sort that allow us to pick out, say, relative size distributions of a PAH population, how much of them have heteroatoms in them, how much of them are ions, how much are neutrals, these sorts of things. There's some really great work from Els Peters in particular along those pathways that I'd point everybody to.
All right, a couple more questions have come in. Next question is from an anonymous attendee. Is there a terahertz spectrometer that can be used to find benzene itself through its ring deformation mode at about 12 terahertz? Or is that region also a mass
12 terahertz, 400 wave numbers. Those are both units I like, but not units that that I have in my head for the acceptable range of receivers of ground-based infrared observatories. So I don't know off the top of my head if there's a receiver that can go poking around for that particular mode, unfortunately.
All right, the next question is from Jihoon Yang, who says, really interesting talk. Interested in the kinetic modeling area. Are these reaction kinetics based on ab initio calculations, experiments, or estimates? And if estimates, how did they estimate?
So I will attempt to answer this without defaming my astrochemical modeling colleagues too much. Most of the reactions that we're going to have to put into these networks for PAHs are based on estimates, and estimates that are more or less saying if it's an ion molecule reaction, we're going to put it at the Langevin rate. If it's a neutral reaction, we're going to try to make an estimate based on the relative dipoles. Most of them don't actually have the quantum chemistry done, much less the experiments. Now, Elsa Cook in our group has done some really wonderful work on the actual kinetics, measuring between benzene and CN, as well as many other researchers, Ralph Kaiser and Nadia Balukhani. And they're going to continue to do those sorts of things. But the experimental measurements on these reactions are incredibly involved, and they take a lot of time and effort to get even one reaction done. Doing it with ab initio is a sort of in between of the two approaches, but the parameter space that we have to explore here, the number of different possible reaction pathways that have to be explored, makes that hard as well. So we have to have some selection process to choose which ones to target. So the answer is all three, mostly estimates, and mostly very coarse estimates. And as Martin Cordner points out in the chat here, by the way, he says that ring deformation mode might be within the range of Sophia's far infrared spectrometers. So maybe Fifi there, or XCs might be the other one.
Yeah, and Jihoon had a follow-up. Do you have any candidate kinetic models to help explain the naphthalene and CN related molecules?
We've certainly put in the reactions of naphthalene and CN into the network. I believe that the current rates that are in there are based off of the rates for benzene plus CN. But don't quote me on that, and I'd want to check with my modelers to be absolutely certain. It would be very nice if there were laboratory measurements done for that.
All right, we have a lot of questions left, and we're after the top of the hour, but I'll keep going as long as I see people here, and as long as our speaker has time.
Sure, go for it.
So our next question is from Christian Borsma, who asks, how large in terms of rings do you think you can go with identifying PAHs?
That's a great question. I think that given the current set of data that we have using the GBT and without occupying 100% of the time on the GBT, we're probably going to cap out at about 3 rings for a relative number, for a large number. We might get really lucky if the 4-ring system comes along that has favorable chemistry and a very large dipole moment. That's conceivable, but I think we're going to be primarily exploring the phase space between 1, 2, and 3 rings there. One of the interesting possibilities for pushing that further comes online in the next decade or so. The next generation Very Large Array will be a synthesis imaging telescope, an interferometer with better collecting power, better sensitivity than the GBT in many aspects, and might allow us to pick apart the signal from larger ring systems going forward. But it's kind of a hope and a dream more than a guarantee.
All right, our next question is from Stephen Ferber, who says, when you originally were stating the percentage of molecules relative to the chemical abstracts, your percentage was based on the vast number of artificially synthesized molecules that have been synthesized by humans, probably heavily biased by benzene, toluene, et cetera. How would that fraction change if you considered only natural compounds that have been detected?
Sure. I'm speculating here, and it's possible that the references that I put on that first slide, and that if you email me, I can send to you, might have done the actual poking around for it. But I actually don't think it would change that much. It's true that a lot of the natural products don't contain pure benzene in them, but many of them, in fact, an overwhelming number of them, do contain 5- and 6-membered rings. They tend to be substituted with heteroatoms like nitrogen, but you can see it looking at the nucleobases in our DNA and the amino acids in our proteins. These all, for a very large percentage of them, have these 5- and 6-membered ring motifs in their structures. So once you get above a certain size, having a ring in the molecule is more of an inevitability than anything else. So I really don't think that fraction will change too much.
All right, we have an anonymous question. Do you expect to see any extremely exotic species in TMC1 that we would likely not see on Earth or in Earth-like environments? And if so, at what point does it become reasonable to search for them?
Yeah, I would say that we're already seeing these. So those cyanopolyene molecules that I touched briefly on as evidence for our models doing well, so HC3N, HC5N, HC7N, HC9N, these molecules are extremely transient on Earth. We make them by striking a discharge in our spectrometer and measuring them before they crash back out again or react away to other species. These are incredibly abundant in these clouds. So a lot of the molecules that we search for are short-lived or very reactive here on Earth. And the only way that we can measure them is in vacuum chambers through supersonic expansion discharge sources or other production mechanisms like that. So I would say a large number of the molecules in TMC1 already known are exotic by that definition. And new detections will continue in that trend, I think.
All right, our next question is from Jess Palco, and this is a very good question for a chemistry audience. Thank you, Dr. McGuire, for a very interesting talk. I often see these units of relative velocity on the x-axis of rotational spectra in the context of astronomy. Could you elaborate on what this means? I'm unsure how relative velocity can be used to show quantized transitions in the same way that frequency, wavelength, and energy is often used.
Sure. Okay, I'm going to go ahead. I hope I've shared switch screen to a whiteboard here now. And I'm going to go ahead and just draw something on here. So what we have is a molecular cloud, and then we have us down here on Earth, right? And the molecules in this cloud are moving away from us. The bulk cloud is moving away from us at some velocity, right? So that's going to introduce the Doppler shift that shifts all of the lines by 1 velocity. But the molecules in the cloud are also moving around within the cloud at some smaller velocity, right? And that smaller velocity contributes to the width of a line. So this line width here, I'm drawing with my mouse, so please forgive the fact that this is the furthest thing from a Gaussian that you've ever seen. This width here in velocity space is primarily due to the Doppler effect from the motion within the cloud itself. All right, now Doppler velocity is a change in frequency. Wow, this is really rough, over some rest frequency times the speed of light. So the Doppler shift, or in other words, the width of that line in frequency space is dependent on the frequency itself. And so the problem arises if you have a spectrum and you have lines down here like we do at 10 gigahertz, they have some width in frequency space. And then you move up here to lines at 30 gigahertz, and their width in frequency space is 3 times the width that it is down here at 10 gigahertz. But there's actually nothing physically different about the molecules that are arising, giving shape to, giving these two different line profiles. And so by converting them to their relative Doppler shifts, all of these lines will collapse to the same width, because that width is due entirely to the motion of the molecules in the cloud. And that allows us to compare line shapes, compare lines at different frequencies exactly analogous to one another. And so we just set this rest frequency here to the center of each line, and that allows us to set a relative velocity, a relative width to that line for that Doppler shift. Hopefully my chicken scratch was understandable, and apologies if it isn't.
All right, and then we have one last question here from Arthur Purser. Are the signal processing methods you have shown effective in lowering the limit of quantitation, and do they translate well into trace quantitation via IR?
I am not entirely sure what the question is asking here, the limit of quantitation, meaning are they effective in making it so that we can see lower abundance species? If that's the case, then yes. A lot of these molecules, especially in our initial data, we weren't able to see their individual lines, so we could never actually measure their column densities because they were too low. By adding up all of the lines together and getting one signal for the molecule, we are able to actually quantitatively measure and pull out those column densities. This same signal processing technique could indeed be applied to the infrared, but it's really not going to help us in picking out individual molecules in the infrared either, just because the aggregate model there still depends on knowing what the underlying molecules are, which we don't at the moment.
All right, well, that is it for our questions today. Thank you again to both Brett and Brent for very stimulating talks, like a lot of discussion. This was a really nice way to have our March AstroCheminar. So I'll remind you all that next month, as I said at the beginning, we will not have an AstroCheminar. We encourage you to attend the ACS spring national meeting, and please also check out Brett's astrochemistry discussions on March 24th. So thank you everyone for coming, and we'll see you after the ACS meeting in May. So goodbye everyone.